So Andrei is a senior research scientist at valeo.ai and INRIA in the Astra team in Paris. He got his PhD at MIN Paris in 2012, did a postdoc at INRIA Rennes and Paris also in the Willow team. In 2016, he moved to industry at Safran Tech to pursue research on autonomous systems. And his current research interests are in computer vision and deep learning, and especially reliability of deep neural networks and learning with limited supervision. So thank you, Andrei, for giving the talk.
Okay, thank you. Thank you for the introduction. So just as a disclaimer, I'm already realizing today across the discussions that here it's a Bayesian camp. So there's a lot of Bayesian people. My talk today is frequentist. I come in peace, just so you know. But we have also works on Bayesian. It's just that for the scope of today, it will be mostly frequentist stuff related to some of the works that we have been going on this area. So just as a background, so I'm a researcher at valeo.ai. It takes a while to talk. I think it's related to the connection. It should be arriving. Which is a supplier for the automotive industry. So we build sensors and essentially everything what's in the car except the car for the car manufacturers. And at the same time, I'm also partially affiliated with INRIA in Paris. If I go back, maybe. Okay, so it might okay. So it had a problem with my slide. That's why. Can you do a refresh? So the fans of everything in the cloud. Yeah. So most of the works that I will be presenting today are with my colleagues. Well, not all of them, but this is my lab where I'm currently working at INRIA. So just a bit to show you what's our objective in the work that we do. I will share with you a video with one of our vehicles. So the vehicle is pretty old. The video is pretty old. It's like 5 years old already. But it's just to show you what's our white whale, what we aim for in our research. So this is a car equipped just with industrial sensors, so it's sensors that are produced large scale, so it's not sensors that cost more than the car, and that we were using with our clients. And here it's the vehicle wandering around the streets of Paris using fisheye cameras for their surround view, lidars. So it's very cheap lidars. We're the only ones having lidars in a large scale production for sensing the depth, and also the planning and all the things that come with. So the video is pretty old. We have a few more advanced stuff, but we don't have yet them in a shiny format. So kudos to my colleagues from the R&D teams that have been working on this. Yeah. So just to outline what we do in the part of the group that I'm attached to. So we essentially develop the eyes and the ears of the car. And this remembers me that I should also take the time. So we developed ultrasonic sensors, near-field radars, surround view cameras for the parking. Scala, these are lidars, so laser pointers that sense the depth around the scene, and all sorts of cameras, long range and short range, inside and outside the vehicle. So where we are at now in terms of autonomy, so you might have seen it in the press. By this year, we have already 2 vehicles that have been certified for level 3 of autonomy. So this means that throughout the time that this vehicle is in autonomy, it's the car that is responsible. But okay, don't get excited too much, because this is in very specific and limited conditions. So it's in roads with a central separator, with a maximum speed of 60 kilometers, and without any pedestrians and cyclists on the road. So it's essentially on the highway when you're in traffic jam. But we're getting there. And both the cars that are equipped with that are certified for that are equipped with the valeo lidars. So you always need lidars and cameras and a big batch of sensors to have these certifications. So why does it take so long to reach these levels of certification? So I'm showing you some examples with things happening in the real world, just with the camera. So as a disclaimer, I'm mostly working on vision. So as the title said, it will be visual perception. So expect a lot of photos in this presentation. So these are really just to show you the diversity of things that can happen in the real world when you deploy a car, a robot on all sorts of streets, weather conditions. There's changes in the weather, in the outline of the streets, in the density of the streets, in the types of vehicles that you have, in the weather, glare, all sorts of perturbations and different accidents that you can encounter that are not generated by you. So the vehicle is expected to cope with these types of situations that are not always foreseeable. So just to show you an example on why this is painful. So here I'm giving as an example. So here we have 4 perception models that are ready to be embarked. So they're deep neural network based, but with performing the semantic segmentation task. So here in semantic segmentation, for each pixel, the network has to classify to decide which class is it. So you have high resolution images, and the network should output these 2D maps, where you can see in blue we have the cars, in purple we have the road, in magenta the sidewalk, in green the vegetation, gray with building and so forth. So here, as long as the image is clean, as is in the training data set, the predictions are fine. Okay, there's some difference in the quality of the predictions, but this is really related to the capacity of these models and the computational constraints. But then we add gradually some rain. So we simulate a distribution shift. So we have here a moderate rain, and we start that some artifacts are starting to appear in the prediction, then some heavy rain, and while everything is messed up, and by the time we get to a shower rain, there's nothing in terms of prediction. So it's all sorts of hallucinations. So this one hallucinates roads, and I don't actually know what class it is. It might be water. It's not very clear what's in there. So these algorithms, these perception algorithms, can be very brittle when we do such distribution shifts. So to recap a bit, in the pipeline that we have for when we develop a product for ADAS, autonomous driving and driving assistance, we have these 3 main pillars of activities. So first, we have the training stage, where you have access to train data, validation data, test data, some test data at the end, and you want to develop your algorithm, your model, which is robust, high performing, calibrated, extends to different domains and so forth. So this is the first stage. In the second stage, we have what we call validation. So I think the synonym, it's not the validation that we have in machine learning, is the synonym would be verification, where you essentially have a data set which is orders of magnitudes bigger than your training set, where you just want to assess the performance of your model, and you also look at different corner cases, and they also analyze the robustness. How well does it generalize to ODD, but also to OOD, to out of distribution samples. And finally, we have the deployment, where the model is not left alone. We have some monitoring to accompany to detect and quantify distribution shifts, but we also have mechanisms to do test time training and adaptation, as you saw with Aditya. He was doing adaptive calibration. So these types of things that allow your model to cope to some extent with what is facing in front of it in the real world. So today, the things that I will presenting today touch on these aspects, on how to have some robustness against different perturbations, what can we do to have models that do well in OOD validation and to robustness validation, and finally we'll be looking at a tool for doing monitoring of deep neural networks. So firstly, I will go to show you a bit the endeavor that we have towards achieving more robust models. So, not new to you, but it's sometimes new to engineers and to people that deploy these systems, is that the world is changing fast. So here I'm using as an example the evolution of men's fashion trends in the 80s, and it evolved quite a bit during the span of 10 years. A car, when we equip it right now with some camera and a software, we expect it to work for 10 to 15 years. Right? Well, you might have heard that Tesla is doing over-the-air updates. So this over-the-air updates are current to premium vehicles. But as these cameras are gradually deployed to mid to low-cost vehicles, you don't have this advantage of having over-the-air updates. So your algorithm should generalize to different settings that will appear in the following years. And also unseen weather conditions and potential sensor aging that you will see in this period. So this was the starting point for one of our works, which is called StyleLess. So if you are familiar with style transfer, the inspiration is neural style transfer. The inspiration is from them. If you're not familiar, I'll just explain it to you in a few words. So in style transfer, we have an input image, and we have a style image, for example, this one with the sunset, and the goal is to transform the input image to have the style of this style image, but without losing its content. So here we see that we still have the car on the highway, but it's as if it was at dawn. Similar here for rainy. We want to convert this image in a rainy scene, but again, without changing the content too much. So in practice, this amounts to a multi-objective optimization, where on one hand, we want to perturb the image, the input image, as much as possible to transfer the statistics, the visual statistics that we have in this image. But on the other, we want to preserve whatever it's inside this original image. So we have two losses. And what's interesting, so one is related to the style. So this measures the similarity between the output image and the style image. And the other one is related to the content. So in the content, what's interesting is that this image with this one, this image with this one, and this image with this one, at the end of the style transfer optimization, have a content loss which is 0. So it means that we have preserved most of the content. Here, this is a dummy visualization. We don't have access to this content. We're just trying to visualize it here, but the idea is that we consider that in this case that whatever changes in weather the vehicle will face, rain, night, dawn, fog, it's as if the style of the content was changed. So we consider it as some sort of noise that perturbed the original content, and we want to train the network to grasp on this content, such that whenever there will be changes in the outside weather conditions, it will be ready, robust to face these, and invariant to face such situations. So how we do it in practice? So we have here your favorite deep neural network. I will give you the freedom to select it. So we train a neural network for the task of semantic segmentation in this case. It can be also detection or some other task of interest. So, and we stop. Let's say we finish training it. It has decent performance. And then we add some what we call styleless layers at intermediate points in the network. These styleless layers are really similar as the regular convolutional layer. So functionally there's no difference in the operators that we apply. It's just that when we train these layers with a certain supervision, such that we remove the style for the intermediate activations. We remove the style as the features are passed through this layer. So I'll spare you the details of the loss, but when we do the style transfer, what we essentially try to do from the style image to the original image, we compute a gram matrix on the features between the two, and we try to align them. So we tell the content image, okay, I want you to have these as statistics as similar with this style image. So we take this idea, and what we do, we don't have here any style image whatsoever. We just want to remove whatever style there will be in this input image. So what's this happening? So we have here a loss that computes the gram matrix at the input over the feature maps of this layer and also at the output, and I train my network to remove this style information. So if these the two matrices are identical at the input, well, I have a big loss. If not, if there's some loss of information, I'm improving here my loss. I'm reducing it. So in this stage, at the second stage, I'm adding these styleless layers. I train my network again for the same task, but here I have a few other objectives related to the behavior of my feature maps at the intermediate points in the network. So to give you an idea on how this happens, so we look at the most affected feature maps and the least affected feature maps, and we can see here that for the ones that, so here's the input and here's the output of the styleless layer, and here's what the residual between them. So we can see that when information is removed, is really things that is potentially irrelevant in the image. So the feature maps here pick on the raindrops and on the fog that we have, and they're removed. But we keep the most essential information, which is related to the contours, the delimitation of the object. So this is what we care to know, to where each extent is the object going and where is it. And when there's no style information removed, so here there's now not so much noise happening. It's really edges that are well, most of the times it's edges that are on the object, so there's nothing interesting to remove there. So there's no style information relevant for them. So in a nutshell, this is what this work does. And then we went to evaluate it on some, well, let's say realistic conditions. They're not fully realistic, but it was a best effort towards that. So here we were looking at some the cityscapes dataset, which contains roughly 3,000 images from cities in Germany and a few in France. And so we looked at that, but we also looked at different flavors of this. So one is corrupted cityscapes, which is here on the right-hand side, where we apply 15 type of corruptions to our images, and each of it with 5 intensity levels. We look a bit at the gradual distribution shift that is happening there. Then we also looked at the synthetic fog cityscapes, where we add, using the depth information, we add synthetic fog, 3 levels of fog density, and same for rain, 3 levels of rain applied to the model. So when we look at a bit when we compare the performance of the baseline method, so the method without this StyleLess training, here it's a very specialized method for robustness, and here it's ours. Results on cityscapes, on foggy, and on rain. In general, we improve overall across the board. There's sometimes, well, there's no solution one fits all on rain. We're sometimes worse than the baseline on vulnerable on vehicles, but overall we're leading to substantial improvements at a very little cost across these different perturbations. So here I have a few more qualitative examples. Here it's for object detection. So here is the baseline in fog, and here is ours. So we can see that we managed to grasp on objects that had little visibility or were not caught in by the original method, like this cyclist here or this car here, and well, this car in the background that was missed because of the occlusions, and also this car which was small and far away. And here I'm showing some examples on semantic segmentation as well, with 3 types of noise: splatter noise, glass blur, frost, and Gaussian blur. And again, our baseline, the ground truth on top, and our predictions. And we see that in general we recover some of the information lost, or the predictions that were lost because the network was fooled by this distribution shift. So summarizing a bit what's happening in this StyleLess layer, it's a really simple method to learn some visual representations. There's no prior sensor knowledge involved, so it can be applied. We applied it also to LiDAR and to radar. And at runtime, we don't have any pre-processing overload. However, well, it's not quite a Swiss knife, so sometimes this difference between style and content can be arguable. For example, in snow, we have snow falling, parts that are covered in snow and are not visible. Is this style applied to the input image? To which extent is the content? So it's well, there's still some drawbacks that we're currently addressing. Moving on next to another. So here we achieved some robustness by tweaking a bit the architecture. So we looked at how can we change our training and architecture to improve the robustness that we have with respect to the distribution shift. In the following, we'll be looking at another problem that neural networks have in terms of brittleness to distribution shift and contextual biases. And we'll be looking at a data augmentation perspective. So what can we do on the data side to improve this? So fortunately, Aditya already talked about calibration. So I'll go faster on this one. It might be known to many of you, but in general, what's one of the main criticisms of deep neural networks is that they're overconfident. So here we have some differences with an old school neural network from the 90s on the CFAR 100 dataset, and we have here plotted the average confidence and the average accuracy. So the average confidence, we take the maximum, the softmax for the predicted class, and we plot it here, and we see that they're pretty well aligned. However, when we look at the deep neural network, we see that the average accuracy is over 90. So the network thinks it's correct by 90%, well, it outputs a probability, well, softmax score of over 0.9. But the accuracy is a lot lower, it's somewhere around 0.7. So this means that there's a mismatch between what the network outputs and what the quality of that prediction. So Aditya illustrated this a bit here, where I'm showing what we call reliability plots, where we in several bins of confidence, we looked at the values of the samples that get this confidence, and we match them with respect to the accuracy that is expected for that value. So as Aditya said, if your network predicts 0.3 and you take all the samples that are with 0.3, you should be having accuracy of 0.3 if your model is well calibrated. If there's a gap, it means your model is either overconfident or underconfident. So that's one of the problems that network has. And in the same time, they're overconfident, I said, when they're wrong. And another problem that these networks have is that they have high capacity, and we run them for many epochs across the data set, and eventually they learn to fit the shortcuts that we have in the data set, and to learn some correlations between the objects to use that to cheat and to give you what we expect from it on this validation set, but not on the real world. So I'm giving an example here. Here we have a street image with semantic segmentation. Everything goes well. Here, this part here is predicted as road. Here we have some cars. We use a GAN at that time to remove the images, the cars here. So we have now an image without cars, and we feed this image to the network, and now it predicts sidewalk. Why? Because it's used to be seeing sidewalk if there's no car on the right-hand side of the image. It has seen with the same car going around the city, it's seen sidewalks, and there, well, it predicted the sidewalk with a high confidence. So the network essentially learned some shortcuts in this data set. So now what we asked in this project, what would my CNN predict now? So what we did, we took the German cities data sets, and we removed all the pixels with a sidewalk and road, and replaced them with random patterns from the nature, like flooding or desert or something like that. So we want to force a bit the network to see what does it predict, and also to evaluate how our predictions flipping based on these changes of context that we might have to some extent at runtime. So here we're piggybacking on advances in the state-of-the-art data augmentation strategy. So some of you might find this very funny. I also find them these types of data augmentations where you mix some input images. So here I have an image of a dog and a cat. I over-interpolate them. And I would do the same with the labels. So the network now sees these weird types of augmentations of blending of images into each other, and is expected to predict the two classes that are in this. So instead of a one hot prediction of one class, now I have the two classes that are combined with the labels, the ratios given by the amount of pixels that are present in the input image. So actually for this one, there's very theoretical foundations related to the vicinity risk minimization for Vapnik, where you cover all the entire space by interpolating between the images if you want. But what's happening is with these models, even though they look a bit childish, they mitigate overfitting, and further than that, they to some extent they address the calibration. So the models that are trained with these types of augmentation end up calibrated often with performances that are close to those post hoc calibration methods that Aditya was mentioning just before. The drawbacks of these is that, well, these augmentations are not aware of object boundaries, and in particular, when I look at this one is among the most popular right now, CutMix, where you crop an image and put it on the other. It does not take any awareness of the object boundaries. And it's often when I put this dog, I also put it with the context. So I'm potentially augmenting this bias towards the context that typical context that objects have. So what we do in this paper, we look at some practices from old school image processing and decompose the images in superpixels. And these superpixels are like segments in my input images, and they are often aware of the boundaries of the object. And what we do as data augmentation, we take two images like that, and we mix them using the segmentation masks as masks for mixing. So I take, for example, if in these masks that I select randomly from here, from this image, I replace them with the correspondent patches from the other image on below, and I get this composite input image, which doesn't make that much sense, but I have exactly the ground truth data from both of the images and annotations, and I train a network to predict these types of weirdly looking content, but with some object awareness. So this is, well, I'm not delve into more details on the training. You can find them in the paper. What's interesting is in terms of results, we accompany this work with what we call out-of-context cityscapes, where we essentially replace all the street-level pixels with these types of patterns from nature, and analyze a bit how are the networks behaving when we have such a drastic change of context for them. So when we look at qualitative results on these, so here I have my image. We replaced the road with sand. Here is the ground truth. So here I had initially road and sidewalk. Here's the baseline. Here's our method. Not much difference. So they're both doing a decent job in the original image. But when I do the flipping, I see that the baseline method is starting to hallucinate stuff. It hallucinates a sidewalk because it's used to seeing pedestrians on the sidewalk. So if there's a pedestrian, it should be a sidewalk. So this can be actually quite dangerous, right? If you say that there's a sidewalk when it isn't, and there might be some other sidewalk in another space. You might have faulty predictions, and it hallucinates also water. And here it hallucinates a building. While in our case, this method actually seems to be invariant to these types of flippings, and it doesn't impact much the quality of the pedestrians, nor it hallucinates other classes out there. Looking a bit at numbers, a thing that we are pushing for in our works, and also the community is starting to get along with, is to look at different metrics. So we have the accuracy, which is measured in terms of mean intersection over union, but we also look at the expected calibration error. So that measures how well calibrated is my model, because this allows us to, in operational settings, to better threshold our predictions if my output scores are actually meaningful. And also we are looking at negative log likelihood, which is also another proxy of overfitting. We noticed experimentally that, well, we noticed that a model might become overconfident silently, with the accuracy staying the same, but at the negative log likelihood during training, actually this is visible that the model is starting to overfit, and this is a metric that we use for evaluation. So when we compare our methods with ensembles, so here we have an ensemble of 4 networks, while our method is just 1 method. In general, we're close to it, sometimes outperforming it, sometimes worse, but in general, we're close by to a method which is 4 times longer to train and 4 times more expensive at runtime. We do a similar experiment as previously on distribution shift, so looking at rainy, foggy, and corruptions, and similarly, well, we're kind of fighting with ensembles, but well, as I said, we have some benefit in terms of computational cost. So moving on to the last part of the talk. So far we've looked at how to improve the robustness of our model. But to which extent do you work on the robustness, or are you invariant at the distribution shift that you have at the input? There's always a tension on how am I robust to this distribution shift, or I want to recognize that it's a dangerous situation and I don't know what to do. So to help with that, we have been looking at a different line of methods that are looking at the performance of the model at runtime. So as I said, we have our unknown scenario at the input, our perception model, we feed it to the driving stack, and at some point, because of faulty prediction at the input, we have faulty distribution shift at the input, we reach potential accidents. So how to identify more upstream incorrect predictions such that that they're likely to cause system failures. So, and this is the subject of this line of work that we call the observer networks. It's very similar with what we have in monitoring. It's just that here we have our neural network that is the one that is trained for performing a task, say semantic segmentation. We keep it as it is, and what we do here, we add another network that can see all of its activations, just a part of it, but in general has access to its internal activations and predicts anomaly score or a confidence score depending on how you train it, or an uncertainty depending on how you train it there. So we train this by showing it the predictions that the target network, the network that we use operational has. We train it to predict the errors that this network will have. So sometimes we have some good samples, some positive samples, some correct ones. In this case, we have a high confidence score, but sometimes we have something that is incorrectly predicted. Here it predicts cat while it has a fish, and we have a high anomaly score, and we train just this network. There is, however, an issue with these types of methods, is that Well, we're in a data dilemma. To train this head, we need another data set, essentially. If we use the training set, our network is already overconfident and correct most of the time, so there's not much to learn. Here, this thing is also a deep neural network, and we don't have, in general, many negatives to look on that. So what we do, we look at some practices that people have on the web and in robotics, where they have their robots and make them fail. So we saw that, well, in operational settings, you have these very tough evaluation settings or robustness tests where you want to stress test your model. So in difficult conditions, simulating distribution shifts. So this is what we also do here, but we look at softer strategies for that, in particular adversarial attacks. So I will not go into details of adversarial attacks. They're a strategy to perturb the input, add a certain noise such that it will fool your classifier, be it a neural network, random tree, or whatever. You can find ways to conduct adversarial attacks such that your prediction will be off. Now, in our case, we are in a semantic segmentation setting, so we care about the 2D information. So what we do, we apply local adversarial attacks. So we generate these random masks and perturb the input image, and we know that our classifier, our semantic segmenter, will be doing misprediction in this area. It's important here to have a random shape because we want to have this as a proxy for out-of-distribution objects. So we want our network to also be able to detect out-of-distribution objects that are not seen during training. And having these types of random shapes actually seems to be working quite well because it's some sort of proxy of a blobbish thing or an object that you didn't see and that you will have at runtime. We tried with squares, with object masks from other datasets. It doesn't work as well as having a random. So what we do here, we have these hallucinations, and this gives us our negatives that we use for training our observer network. We know here that the network will be wrong, and here we have negatives to train our observer network on hard samples. So this is at train time, and at runtime, we have our segmentation network in our observer network, and one predicts the semantics, and the other one predicts the confidence and the accuracy, the confidence of the predictions. So here, I'm showing some results on some different data sets. So here we have BDD anomaly, some images from the US. We remove from it all the images with train and motorcycle, and at test time, we keep those as an unknown object. And here it's a synthetic data set where at test time we add all sorts of weird objects to see how is the network behaving. We have the baseline scores. Again, we are looking at an array of metrics, and also comparing with ensembles and some Bayesian-like ensemble methods. And again, our approach seems to be narrowing by. It's not always the best, but doing decently with respect to the trade-offs that we have in terms of cost and in compute. Some qualitative examples here. Here we've injected some animals in this data set to simulate OOD, and we see in the uncertainty maps that they are reflected as high uncertainty areas. We still have some other uncertainty areas related to electronic uncertainty or to some other types of nuisance, and that we also detect. But in general, the focus here was for these out-of-distribution objects. Here, the motorcycles here, and this is another electronic uncertainty case happening here with the reflection from the car. So wrapping up, here we leverage adversarial attacks to find blind spots in our target network. So we propose this method which doesn't touch your target network. It can be applied as an observer, a monitor to any network that you may have, and we can potentially generate infinitive negative examples. There's of course some drawbacks that we're addressing them in subsequent work, that we cannot actually localize precisely these areas with uncertainty. We have these 2D maps when in fact we care about the object that is uncertain. And the error score, the confidence it's not specific to a certain type of uncertainty. So we cannot use it to take to separate it between aleatoric uncertainty, epistemic uncertainty, and things like that. It's a generic prediction score. And I had some slides that will be useful for the roundtable, and I will be concluding here for my talk with these two BC types of approaches.
Thank you for the nice talk. So since we're slightly late on schedule, I suggest we take 2 questions at most, if any. Yeah, there are some.
Just a question about the StyleLess. How do you define the style? It's a prior, or you automatically define the style?
Well, it's some sort of prior or inductive biases, as it's in the community. So the thing is that we're completely agnostic to it. So we look at the information, like maybe you press escape?
Because we use the weather, the fog, the sun, 9 day. So this is some prior, but
so we consider it essentially as some noise in style. But I'm just recapping on what's happening in style transfer. So in style transfer, you have the style image, the content image, and the current image at this point. So you essentially iterate over your network, and you do gradient ascent, but you change the image, you don't change the weight. And at each moment across the layers, you align essentially the gram-based statistics of the feature maps between the style image and the content. And at the end, you also have a loss to have the same content and same classification as for the original image. So what's happening is this is the information that we are removing. So we suppose that whatever is style information, it should be encapsulating there. So we don't care, we don't use any style images whatsoever for this. It's completely agnostic. So
thanks.
Another question? So if not directly, I suggest you think about more questions for the roundtable, and we have a coffee break now. Thanks again.
Thank you.